Elena Zannoni. I work at Oracle. I'm in the Linux group. So what I'll be talking about today is a little bit of an overview of the tracing tools that are available in Linux. Some emphasis on the newer stuff that has happened in the last few versions of the kernel and what's coming up. And so let's get started. So at the beginning, I want to talk a little bit about the infrastructure and the building blocks that are available on Linux today to perform tracing, and they're used by all these tools. Can you guys hear me? Okay. So basically, we have, three. Oh. All right. Yeah, I can. Yeah. Thanks. Okay, so basically we have three different types of building blocks or infrastructure in the kernel: Kprobes, Tracepoints, and Uprobes. So let's go through those in that order. So Kprobes allows you to do dynamic kernel tracing. What do I mean by that? I mean, the terminology here is not really always the same. So when I talk about dynamic tracing, I mean tracing that is taking place on an executable where you don't have to recompile, you don't have fixed trace points, and you can actually decide on the fly, kind of like a debugger, where you're going to put your trace points and what to collect at the particular trace points. So basically, you can do this on a running kernel. You have to configure Kprobes in when you build a kernel, but beside that, you can actually put your trace points anywhere you want. So as I said, similar to debugger breakpoints, you insert a breakpoint instruction at a specific location, and then when the exception is caused, the handler actually will execute the actions of your probe, which usually are collecting variables and calculations and stuff like that. There are some optimizations that have been done during the years that Kprobes have been in the kernel to allow jumps instead of exceptions. So basically, the path has been made as efficient as possible so far. These are used, as I said, by systemtap, by Ftrace and Perf, and the other tools mostly support those two. Alternatively to the dynamic tracing, we have what I call static tracing, which is basically if you want to probe at certain points in your code, you have to instrument your code ahead of time. So basically, there is static points in the kernel code where there are particular constructs, and those constructs are used by all the tools. So they're kind of agnostic of what tool is using these constructs. They are constantly being added. There are about 1,000, I believe, right now in the kernel itself. All the details are in the file tracepoint.h if you want to take a look at that. More details, they basically use macros, trace event, define event, and declare event class. They have similar purpose, but slightly different, whether or not you have one single event or multiple points to probe, where the events are kind of similar with the same parameters. So you can actually declare an event class and have some sort of an instantiation of the class at the various points. So you define these events, and then in your code, you actually use this function that starts with trace underscore and then the name of your event. So you can correlate. So for instance, in sched.c and sched.h, you can correlate the definition of the macro and the use of it. And all the stuff that has been defined will be in include trace event subdirectory. So there are many .h files there that have all the events that are currently in existence in the kernel. Alternatively, if you look at, for instance, random.c, you can see that there are definition of a class of events. So that can give you two examples of how to define trace points in two different ways. So the other construct that we use is Uprobes, and this one allows tracing of user space applications. This was like one of the latest things that have been added, and by latest 2007, but this was started like in 2005 basically with Kprobes. So things have been building on top of each other. And this allows you to use, as I said, to probe Userspace apps handling breakpoints inside the kernel. So the mechanism is similar to the Kprobes: insert a breakpoint instruction, catch the exception, do whatever you need to do. And you are allowed to have different tracers on the same point. It's not that you just have to have one instance. So let's look a little bit at the details of how these are actually implemented. So first of all, you have to configure those in, just like with Kprobes. Their implementation is based on inodes because, after all you're saying is you're trying to identify a location into a file. And so that is a perfect way of doing it, using a data structure that's already in existence. So you can register a Uprobe. That means you can add a probe, and then you can add observer or users of these probes, and you can have multiple consumers, okay, for each of the probes. You can do all sorts of tricks. You can execute them all the time that the instruction is reached, or you can only do them if certain conditions are satisfied, etc. So this is just a basic building block. Then all the syntax and the way that these are used varies from tool to tool, and you can do very complicated things, as you probably know by now. The latest in the family was Uretprobes. That is basically a way of placing probes at the exit of functions in Userspace code. At the exit of functions in Userspace probe. And it is done in two steps. You place a probe at the entry of the function. When you reach the entry of the function, only then you actually go in and insert the probe at the return, which would be actually the return location in the caller. So where are we status-wise with this implementation? So as I said, they're supported with Perf, Ftrace, and systemtap, and others right now. Uretprobes was the latest addition in 3.10. Systemtap has been supporting those. The architectures for which they are there is x86, x86-64, and PowerPC. There is current work going on for ARM. If anybody's interested, there's a link to the tree. They recently posted a new version of the patch, and it's going under review and revision and stuff. The Uretprobes are still also a little bit, behind, but they're coming. So let's look at the actual tools that you can use to do the probing, and they provide an abstraction layer on these fundamentals concepts that I showed you. So some background. So we start with Ftrace. This was like the first one to be into the kernel. So it started in 2008. It's maintained mostly by Steve Rosted. There are various trees where you can find various pieces of it. Basically, there are 3 different ways which the user can talk to Ftrace. You can use files into the debug directory and echo commands into those files, and those will be read and modify the behavior of Ftrace. You can use trace command, which is a command line tool, and at the end of your collection of data, you can visualize the data using a GUI that's called Kernel Shark, which is quite interesting as well, and it allows you to zoom into different time intervals and different granularity, and also highlight different type of events with different colors and stuff. So it's quite interesting. There is quite a bit of documentation right now in the kernel tree regarding Ftrace in general. The main 2 files are listed there, but there are others for all the commands and stuff that's available. There are many articles on LWN and so on. These are a little old, but it gives a good introduction. So again, there are lots of config options, config options when you build and configure your kernel to have Ftrace, and most of them also define what tracers, what plugins are available. Some of those are enabled by default in the Fedora kernels at the moment. So you can do a test run or try it out but without having to rebuild anything. So basically, as I said, how do you control ftrace? If you look at this debug tracing directory, it has output. It has files that allow you to specify the behavior of ftrace. So, for instance, I just list a few here. There are many more, and we'll see later. I specify a few more later. So, current tracer, which tracer is in effect? Like, what are you tracing, functions or other things? Tracing on, you can turn on and off the tracing by enabling the write-in to a buffer or not. There is a file called trace, which is your output buffer, so where all the data gets stored from your tracing. You can do live tracing if you use the trace pipe file. There are files that list available events, available tracers, and there are files that are used to define dynamic tracing points on top of the static tracing points that I was talking about before. Then there are some directories there, some of which I'll talk about it in a little bit. So what can you trace with ftrace? Function that will trace the entry of all the kernel functions. Function graph, you can trace entry and exit to the functions. Therefore, you can actually construct a call graph. You can look up latency, interrupts, preemption, and you can also decide to trace nothing in case you want to interrupt the collection of your data. So which tracer is in effect is controlled by this current tracer file, which I talked about before. So you can have fun and enable all sorts of different things there. So as I said, you can do dynamic tracing with ftrace. By this, I mean you are allowed to define probe points on the fly in your program without having to use precompiled locations where to collect the data that you are interested in. So you can do both Kprobes and Uprobes, and if you go and look in this magic tracing directory, you will see that there are files that are called Kprobe events and Uprobe events that will store the information regarding which dynamic trace points you have enabled. And again, here the syntax gets very complicated, sometimes a little bit Byzantine in my opinion, but there are lots of things you can do. There is some documentation, there is articles, and here are some examples of syntax. So the first one sets a return probe. So at the end of do sys open, print me or collect me the return value. And so this syntax is echoed into the Kprobe events file. You can also do the same for Uprobes. So if you want to put a probe in bash at that particular address, then you can store it into the probe events file, and then ftrace will go and read those files and do whatever it's told to do. And you can clear them by echoing nothing into the files. So pretty straightforward. The challenge, I would think, here for the user is to remember all the options and all the very little finicky syntax. So an aid to that came out when Steve implemented this trace command Userspace tool, which is another cover on top of the ftrace engine that allows to be a little more usable and user-friendly to define all these behaviors. So you can say trace command record, report, start, stop, extract, list, and you have a little bit of transparency on all the complexity that you have under there. Steve just released, or at least tagged, the 2.3.0 version last week, actually this week. And you can find it at that location. Again, you can read articles on that. There are, help commands that you can use to look at some of the stuff. So basically, this also allows you to do the same stuff that manipulating the files directly into the tracing directory will allow you. It's equivalent. So what has happened in the 3.10, 11, 12, 13, the latest kernels in ftrace? So first of all, this is just a list. I will go through those real quick. So we have instances, function tracing triggers with many controls, options, and parameters, more trace clocks, and different options to disable the collection of entry and exit for specific functions. So if you want to avoid tracing some functions when you're trying to collect a graph, call graph, you can do that. And then you can actually stop the tracing at the point of a warning. So if you're looking for some specific and then things go bad and you're collecting maybe too much data and you want to stop it exactly at where the warning is triggered, you can actually do that. So as you can see, and I'll emphasize this, the trend before was to build all the infrastructure, collect all the data. Now the trend is, whoa, it's too much. Let's thin this down. So all the options that you're going to be seeing are kind of to narrow down and kind of filter all this output. That has been the emphasis in the last cycles of the kernel. Again, updated documentation, and the newest stuff, which is actually will be in 3.14, is the event triggers. So what are instances? Basically, instances just allow you to channel the data in different subdirectories. So if you look at the tracing subdirectory, there is another directory called instances, where under there is like almost a duplicate of the top directory. So you can have different instances of tracing going on, and each of them will put the results in its own buffer in a different subdirectory. So again, you can channel things and divide them. And they're pretty easy to enable by make directory and remove by remove directory command. They will automatically populate the subdirectory for you. So that has been one of the biggest things that happened recently. Then again, as I said, filter on functions. Again, you don't want to trace all the functions that you have in the kernel. So you can specify which functions to use for tracing or to collect information about using using these tracing filters. So you have a list of functions that you can select, and that's in the available filter functions files, always in that magic tracing directory. And then you can actually enter stuff into a file that tells you, okay, these are really the ones that I want to look at. Or you can also enter information in a file that tells the Ftrace to absolutely don't look at those. Those I don't want to know anything about. Everything else is okay, but not that. So you can, again, echo what you are interested in into these two files. Here I have an example of, stopping the trace when a certain function foo is reached. And so you can add this syntax, this command, subcommand, trace off, which will turn off your trace if that specific. So it's like a conditional tracing or untracing. And then when you want to turn off one of these instances, and this is pretty consistent throughout all the filtering syntax, you negate it in front, right? And that will just disable it. So as I showed you before, at the bottom of the slide, if you see, basically, if you reach foo, do something. So this thing is called, also known, is called function triggers, right? So basically, do something specific, start the tracing, stop the tracing, enable something else, collect something when a specific function is entered. So this is pretty simple concept, and the syntax is not too complicated, but it can have, again, a lot of different options. So you can specify, enable something when a function is entered. You can say, do this for the first n times that a function is entered. Or you can disable some event from happening when that function is entered. And so here I have some examples of things that you can put in your filter. And again, if you want to operate on events itself, enable events or disable events, they have to be one of the ones that are defined in the available events. And those can be your static trace points that Ftrace can see that were in the kernel, or you can be the events that you have defined yourself through Kprobes. Okay, so again, you can do, as I said, things get complicated quite fast, and you know, it's not a bad thing. It's just remember all these options is the challenge, but it's really, really flexible, and you can do a lot of stuff. As I say here, you can do a stack trace, so you can collect a stack when you enter foo, or you can do that for the first 5 times that you enter foo, or you can just disable the whole thing. You can also save a snapshot of the trace buffer, or you can dump the snapshot of you can dump the contents of the trace buffer to the console. So there are many different, you know, little variants, and I think this kind of also evolved, you know, when Steve had to debug something and needed a feature, there it goes, which is good. So the new stuff that's coming in 3.14 for Ftrace, the big thing is these event triggers that Tom Zanussi did. They are right now in the for next, you know, inclusion for next. So just like, kind of like the function triggers, these are do something special, enable another event, you know, when a certain event happens. So in a sense, you say, what's the difference between a probe? You know, do something, collect information when a specific location is reached. But this is at a level above. I would say this is kind of a meta level, because here you are like, an event occurs and this one enables another event. So here you're modifying the behavior of Ftrace itself. So it's another level of indirection. And so here again, you can have a bunch of triggering events. And again, there is another magic file called trigger, which contains the rules for these triggers to happen. For instance, here you can do, if you're interested to enable something when the read syscall is happening, you can put your trigger, which will be your commands to do, in this particular file under the event, and then syscall sysenter read trigger. So for instance, the example below, I say collect a stack trace for the first 2 times that the read system call is entered. So again, this can become a bit more complex. It's not just the stack trace that you can put in there. You can say enable another event, disable an event, collect a snapshot, start the tracing, stop the tracing, and as I said, counts and also condition. There is also an if syntax is allowed. So this is the summary, very generic, you know, it's not even scratching the surface here, but, you know, can get a flavor for, you know, if you're interested, there is a lot to read. So the other main tool is Perf, which started a little later, and it evolved on top of perf counters. It is now becoming bigger and bigger, encompassing a lot of things and a lot of subsystems in the kernel. So as I said, these are, you know, many big contributors. There is the documentation is a little, I wouldn't say sketchy, but, you know, they're not as good as keeping the documentation up to date as they are, you know, improving the code, obvious. But there is a wiki, there is a user guide, which also is probably from 2012. So, you know, things have changed, but it's a good starting point, both of those. And if you want to look at the code and what's coming, it's actually Arnaldo that maintains it and collects everything, you know, so you can look at history there. So just again, a little, you know, very 10,000 feet view. Of the various subcommands. So this is similar to trace command, which is actually the opposite because trace command was modeled after perf in a sense. But you have a main command perf and a lot of subcommands that allow you to do a lot of stuff. You can statistics, you can print, you can record into a file. You can then report what you have recorded into the perf.data file. You can do differences and see what has changed between maybe 2 consecutive runs of the same thing, and you can find what the different outputs were and where things went different. You can do live performance checking. You can, of course, do the dynamic trace points, as I said before. You can do system call, collection of system call, entry and exit parameters and return values, and you can use scripts to manipulate your data that you have recorded. So it's pretty powerful, and this is just a little bit of the commands. Again, you can list the events that are available. You can look at logs, scheduler behavior. You can do KVM monitoring, so it's really, really powerful. What can you observe, quote unquote? So basically, if you do a perf list, you'll see a bunch of the stuff that you have available in terms of events. But basically, you can do the trace points, the bottom 2 parts, the static trace point, like the ones that I showed you at the beginning, dynamic trace points that you, user, have defined for the specific run, and then all the stuff that are, in various counters and registers. You can use, you can look at that stuff too. And again, all is defined as this file called perfevent.h. So if you want to really look at all the stuff, it's all in there. There are ways of narrowing what perf is looking at. So this is kind of a way of focusing on a specific type of target or a subset of what's going on in your system. Thread-specific, system-wide, focus on a specific CPU or a specific process. So there are many, again, variables in play here. So I'm not going to go through all of those. As I said, you can do dynamic tracing with perf as well, and you can use the command Perf-probe, and you define the, as you see at the bottom, you can define a probe for a specific executable, which in this case is, Userspace. And you can add a probe, delete a probe, and do a dry run without actually running your program. So it's, again, perfprobe.txt is the file that has somewhat explanation of what this particular stuff does, which is, same. The interesting thing here is that you can actually use the debugging information to set a specific probe at a specific location and also to collect the values of specific variables at that location. And this is kind of important in terms of the history of this whole section of the kernel and how we got here. So some recent improvement, again, 3.10 and forward type things. You can do, use different methods to look at different data output files from different runs. You can group the events and show them in a, more user intuitive way. Lots of bug fixes. You can now have there is a subsystem that looks at memory access. There is a talk that Namyam Kim did in sometime in 2013, in the summer, June 2013, and that has some of the latest examples if you want to look at that. So another thing that's in the works right now is this integration between Ftrace and Perf. So this is, again, interesting in terms of the history of these tools because we have infrastructure that is used by both tools, which is kind of, duplicated, but not really, because different tools have different needs. So there's been talks for the past, well, I don't know, maybe a year or two ago, about integrating this infrastructure, like the buffers and stuff like that. That never went anywhere after a few, interesting debates on the kernel mailing list. So the infrastructure is likely to remain kind of separate, except for the parts like, the Tracepoints and the Kprobes and the Uprobes stuff. But the rest is kind of all tool specific. But now we're looking at integrating the top level. So at this point, we would, the proposal was to have Ftrace become part of Perf. So that you can say perf ftrace and have the same behavior as of ftrace by itself. So there was a few patches, as you see, 5 versions of them were sent out. But now, at the moment, this is kind of stopped, and Namyoung is going to come back to this eventually. But there was a lot of commenting, and initial idea was to have, perf trace record, perf ftrace show, report, and live. And those were the first ones that were implemented with this set of patches. So look at this will come back. It's not permanently stopped. I'm sure they will figure it out. And again, some of these commands repeat the structure of the perf commands, where you can actually specify what to trace, a specific CPU, a process, system-wide, and so on. And then, then you will be taking advantage of all the infrastructure that's in Perf for showing stuff, like a lot of the nice histograms and other things. So there is quite a lot happening there. Another thing that started and stopped, but it was promising, was support for STT markers, which are the markers that DTrace uses. So they are actually statically defined markers, but with a different syntax. Systemtap is supporting those through some, conversion layer. There are a bunch of patches. This is also stopped. Sometimes that happens, right? People are pulled in other directions, but that was also quite promising. Another one was from Jiri, which is one of the main people working on Ftrace, on Perf, sorry, to do some toggle events. So it's kind of like the triggering idea. And again, this also is kind of on hold at the moment, but I'm sure it will come back. So this is kind of the very quick overview of Perf. Some stats, if you're curious, nothing exciting here, but just the number of people. I started collecting this when there was kind of a, Perf, Ftrace was kind of divided community and stuff, and so I started track. So every year I keep adding, and it seems to have stabilized in terms of, Perf has a little more contributors, but Ftrace is not, it's not dead by any means. So a quick look, I have 5 minutes here, should be okay. A quick look at other tools that are floating around. They're not part of the kernel itself, but people use them. So we have Ktap, systemtap, LTTng, and DTrace. So Ktap is new. It's not in the kernel at the moment. It's been brought forward by Jovi, which is at Huawei in China. It all started this year, and it's still working on features and things. People got quite excited about it, so much that Greg put it into the staging tree, and then there was like, whoa, wait, we haven't reviewed the code. And so the thing got pulled. And so there is quite a lot of cleanup and things that they've been asked to do, but it hasn't happened yet. And in the meantime, they've done 2 more releases. So will this happen? I hope it will, but So it's basically the idea similar to DTrace. This was actually done because of the embedded community. They needed something a little more lightweight. So it's interpreted, there is an interpreter based on Lua, the language, the scripting language, sorry, to define the action. So the concept is always the same, right? Go somewhere, you know, put a probe, execute something. The way this is done varies, right, from tool to tool. So in this case, you write your script of what will happen at a specific location, and this is interpreted inside the kernel. So there is no requirement, as opposed to systemtap, which we'll see in a couple of minutes, there is no requirement for having GCC around, so people are, you know, rather excited about it, and it's fairly lightweight, so it was well received, but right now it's kind of like, again, in limbo. A few weeks ago, there was a new proposal by this person, Alexei Starovoitov, who decided to reuse the Berkeley packet filtering stuff to write filters for tracing. So I don't claim to understand this very well, but there is the link here. You can go and look at the discussion. Again, lots of discussion. He extended the state machine for the BPF to include more complicated things. He extended the number of registers, the instruction, and so on. He can also, instead of writing programs directly into the BPF format or instruction set, you can actually write them in C. There is a backend in LLVM that will translate those in BPF instructions. And there is a backend in GCC. The backend in GCC is not in GCC. I mean, it is maintained by him on GitHub somewhere, and the LLVM, I believe, is actually included in the LLVM compiler. So then this discussion where everybody, again, was excited about seeing this new approach, or maybe we can use it, we can integrate it with Ktap, and then it started derailing, you know, oh, well, we can include GCC in the kernel. So that's kind of where it stopped. So the discussion is quite interesting. Again, promising, but right now it's still, you know, it's fairly new, just like a month old. So then systemtap, real quick, one slide per tool. Again, this is all started in 2005. This was like the first thing on Linux when Solaris was doing DTrace, right? And this is how we got the Kprobes put in and all that stuff. There's always been some controversy around systemtap because of the use of GCC, the execution of, you know, it creates a module, the modules get inserted into the kernel. Oh my God, is that safe? Maybe not. It needs a debugging info. We don't have the debug info from the kernel, so there was a lot of controversy there. While right now we're actually seeing that Perf itself is actually supporting the use of the debugging information. So things have changed since 2005. The community has become more receptive about having more tracing infrastructure into the kernel. At the beginning, they really didn't want any of that. LTTng, also tools outside of the kernel, been around a while. This is continuing. People are using it. It's in some of the embedded distros. They keep making releases. The community is quite alive. So that's another alternative. I'm not going to go over that. DTrace on Linux, that's my group doing that. I have to, you know, I have to mention it. It's out there. We're almost running out of time. So anyway, this is also totally compatible to the Solaris DTrace. We are making sure that the syntax of the disk scripts doesn't break, and that, you know, as much as, you know, things are meaningful on Linux as they are on Solaris, some things are not. So there's been quite customer demand and also internal to Oracle, so we've started doing that. It's available with the unbreakable kernel, which is 3.8 based, x86-64 only. So if people want to take a look at it, it's there. Unfortunately, we have licensing things that they're not going to change as far as I know. So the kernel changes are GPL. There is a DTrace module, which is CDDL. But it's progressing, and you know, we have seen used inside Oracle. We're integrating it with PHP, just like the Solaris version, and now with MySQL, just like the Solaris version. So we're slowly moving forward on that. And I have an example. So we can do Userspace probing. I'm not going to go through the example because we're basically running out of time. One last thing, and actually instead of you asking questions to me, I wanted to ask questions to you of basically, are you using tracing today? Do you find it easy to use? Are we hitting the mark there, or are we still like in our little sandbox? Yeah.
Only one I've had much depth with so far has been Perf, and it's pretty seriously impressive. The main challenge has been that it can be very difficult to bridge the kernel space user base divide, especially because only some builds support any kind of user space dwarf reading.
Yep.
So I often have to read all Perf with dwarf patches before I can actually do anything that traces from kernel space back into user space.
Yeah. That's
so
one of
them. Intense frustration at the moment, and nobody appears to be working on porting Perf to the ELF utils.
Yeah, it's the dwarf stuff. It's been done separately. Yeah.
Anyone else?
I've only one comment, which is that it seems on Solaris DTrace is reasonably accessible. It seems that on Linux, once you go past Ftrace, that is not the case. That's been my feeling. That may just be used for tooling and documentation, but we'll see if that works.
Yeah, DTrace is, we're starting, there is a website, but it's accessible to customers of Oracle. So right now we're trying to make it accessible to a few more people in order to, but it is just starting right now. So we're slowly implementing the functionality, so it's not equivalent quite yet. So yeah, it's a manpower issue as well to kind of, try to do more exposure, to give it more exposure, but.
So the question was?
Oh, about DTrace and the availability of DTrace, which is, on Linux.
Easy to use for people.
Oh.
DTrace seems quite easy to use.
Yes. Yes,
but
yeah.
Tracing on Linux beyond Strace, not so many examples, hard to use, very often not in kernels, that sort of thing.
Oh, I see. Okay, yeah, that's why we ported DTrace to Linux, because that's the feedback we got from our customers. I wish it would be a bit more openly available, but that was exactly one of the reasons. Yes.
Sorry again. Just another one quickly. With Perf, when you're poking around in the memory of Userspace binary, you can't currently capture globals and things. Is that possible with Uprobes or any of the other tools? So when you hit a trace point, you want to capture the state of the global or a local variable like that.
You should be able, if you know the location of the variable, yeah. And if you have the debugging info, even better.
I think we've got time for 2 more questions from the audience. If there's any other questions? Otherwise, please join me again in thanking